Welcome back to part B. So in part A of the video lesson, we went through the alkenes portion and we talked about why we need to use the cis and trans prefixes when we're naming them, mainly because the bond doesn't rotate. So the position before and after the double bond will affect the properties, solubility, melting, boiling point, and reactivity. Alkanes are a bit simpler, alkynes, sorry. So we've got the general formula, CN H2N minus 2. So for example, if we want to talk about a 4-carbon alkyne, we're going to multiply that by 2 to have 8, minus 2, we'll have C4H6. And that's a great general pattern to recognize what type of molecule it is. So alkynes, are linear hydrocarbons. We'll see why in a second. They're the most reactive because the bonds are the most unstable. We've got a lot of electrons in a small space. So there's a lot of potential energy built up. And on the other side of the carbons, because each one is only AX2, that gives it the linear shape. These are also considered unsaturated hydrocarbons, and they do not have isomerism because they are unable to rotate and they are linear. When we're drawing them, we'll use the YNE ending. Hopefully you're starting to see the pattern with the different types of hydrocarbons. So let's jump into it. Our first molecule that we have is 1-chloropent-3-ine. So I can identify the parent chain. It's the last prefix from the right. So if I've got prefixes on the left, those are going to be branches or alkyl groups. But the last one before the end of the name is the parent chain. So I'll start off with this. Because I see the 3-ine here, I'm not going to go right to a full line diagram. I'll draw carbon 3 and carbon 4. I'll just kind of label those here. So I know that because there's 5 carbons, there's one more here, and there must be 2 more in front of this one. So now if I wanted to draw this as a line diagram, it would start off like this. There's my double bond. I've got to go 1 past there. I've got to go 1 back here, and either up or down. So we can see the carbons 1, 2, 3, and 4 make up the triple bond, and then finally 5. For this one, we've got only a chlorine group on the first carbon. We can put that at any position, remember, because it can rotate. And then we have to saturate the rest of the carbons with hydrogens to finish this off. Because the carbons of the triple bonds are saturated, they have 4 bonds already, we don't add hydrogens. And maybe you can see why that makes them so reactive. There's this large open space for molecules to come in. There's a lot of potential energy where those 3 bonds are from all the electrons, so there's bound to be something to happen. If I was drawing this as a line diagram, I would just add the chlorine off of the first carbon. And remember, this point right here doesn't count as a carbon because it terminates in something else, but each bend does. So let's go with something a little more complex here. There's a lot. So if I need to identify what the parent chain is here, I'll start by scanning from the right-hand side until I see a prefix. Okay. And I don't see that until oct. So I know I'm working with an 8-carbon chain. I see double bonds and triple bonds in here. So maybe the first thing I'd like to do is draw this out linear. I don't have cis or trans in this example, but if I did, those would have to be with the numbers for the double bond. So we would write that in this case if we were to show both cis 3 trans 5 diene. That could also be cis 3,5 diene if it was both. So that's just going to affect. And remember, each double bond has its own isomerism. So if you'd like a challenge, try to draw this one where it's cis on carbon 3 and trans on carbon 5. But for now, we'll just draw an 8-carbon chain. So I'll start off here. 1, 2, 3, 4, 5, 6, 7, 8. Before I go right to a line diagram, I just want to sketch out where my bonds are going to be. So I'll number this from left to right when I'm drawing it, just because that's what I naturally think. So on carbon 1, I've got a triple bond, which is good. That means there's just a hydrogen on this side. On carbon 5 and 7, which is here and here, I've got a chlorine group. We're just going to draw these up or down at this point because they're single bonds. Carbon 3 has a double bond to connecting carbon 4, and carbon 5 to carbon 6 also has one. So in this case, you can see that the cis or trans would make a difference. And looking at that name, I've got 2 double bonds, I've got a triple bond, and I've got the 2 chlorine groups here. So all I need to do now is saturate each carbon with hydrogens that doesn't have 4 bonds. And I've drawn the structural diagram. I'd like to convert that to a line diagram, so I'll start like this. Okay, that first one has to be linear. So from carbon, this is carbon 1, that's carbon 2, carbon 3, 4. After this, between carbons, we draw, I'm just going to get rid of this right here, clean this drawing up a little bit. And that's why it helps to have the structural diagram drawn out. So we've got carbon 1, 2, 3, where our double bond is going to carbon 4. So if I draw this out here, this is carbon 3, and that is going to bend. So from carbon 3 to 4, I should show that on an angle. Then we'll level it out to carbon 5. So there's carbon 4. Carbon 5 is another double bond. So if I wanted to show that in a different direction, for example, I could do that. Carbon 6 has nothing on it. It comes out of the double bond. So I can see carbon 5 there, carbon 6. Carbon 7 has the chlorine on it. So if I want to keep going, I can do the chlorine there, and then I've got to go to another carbon, which is just going to be the end. So that'll be carbon 8. Now I might want to clean that up a bit, so I'll go here. And there we go. There's our final structure as a line diagram. Both of these are acceptable, so just make sure you're comfortable understanding them and that you can draw one fairly quickly. When we look at this, the cis and trans, in this case, if I just do a quick little dash line between it, not there, hopefully we can get rid of that. Can't do that dash line there because there's no double bond. So hopefully you can understand why I'm getting rid of it. So this first double bond, I've got a hydrogen on each carbon, which makes it easy. The hydrogens are on opposite side. So the first one in this case is trans. Same with the second one, because the hydrogens are on opposite sides. So the heaviest chains are on opposite sides as well. Be sure to review the alkene video if you're unsure about that. So if I wanted to draw this as the cis isomer, so in this case, this would be trans 3,5-diene, just to put that into the middle of the name. So if I wanted to draw it cis, I would need to rotate this bond up here. So I would start at that point. I would keep this one the way that it is because we said that's already trans. And then from this point, I'll have the double bond going like this to another carbon. And that one will kind of go right through like that. So now when I look at it, right, we've got, in this case, we didn't get that one quite right because the hydrogens are still on the opposite side. So we're going to redraw this one here. So if I've got the double bond coming down, I want to keep that in its position. And I want the hydrogen to go up so that the hydrogens are on both sides. So in this case, all I would do is bring that down like this. So you can see that it gets a little bit tricky to draw the more you add into it. We're not going to focus on these, but they're good challenges. This would be cis 3, trans 5, diene, and then the rest of the name before and after that. And then the one that we drew over here on this far side would be trans 3,5-diene. So hopefully you can see the difference between those. The alkyne concept is not difficult at all, just remembering to keep it linear and using the YNE ending. So good luck. Remember, check the molecule generator moleview.org to help you with the shape of these big complex molecules, and that'll really help you to start visualizing where the shapes come into play.